There is a growing assumption in modern computing that 16 gigabytes of RAM is the new baseline. Marketing reinforces it. Hardware manufacturers normalize it. Many mainstream operating systems seem to demand it just to feel comfortable. Open a few browser tabs, launch a productivity suite, maybe a background update service or two, and suddenly memory usage climbs into double digits. In that environment, it's easy to believe that anything less than 16 gigabytes is outdated. But Linux challenges that assumption in a fundamental way. The truth is that Linux doesn't need 16 gigabytes of RAM to deliver a smooth, responsive, and capable computing experience. In many cases, it thrives on far less. Understanding why requires looking at how Linux is designed, how it manages memory, and how its ecosystem differs from more resource-hungry platforms. At its core, Linux is built around efficiency and modularity. The Linux kernel does not assume a fixed hardware baseline. It was designed to run on everything from embedded devices with extremely limited memory to massive servers with terabytes of RAM. That scalability is not an afterthought. It is embedded in the architecture. When Linux boots, it loads only the components required for the system configuration. Drivers can be compiled as modules and loaded on demand. Services do not automatically start unless configured to do so. This approach contrasts sharply with systems that preload a wide array of background services, telemetry systems, and graphical components whether or not the user needs them. Memory management in Linux is another critical factor. The kernel uses advanced virtual memory techniques to allocate, reclaim, and optimize RAM usage dynamically. One of the most misunderstood aspects of Linux memory reporting is how it uses free memory. On a Linux system, unused RAM is considered wasted potential. The kernel aggressively uses available memory for disk catching, buffering, and performance optimization. This often leads new users to believe Linux is consuming large amounts of RAM, when in reality that memory is readily reclaimable. If an application needs it, the cache shrinks automatically. This intelligent balancing act allows Linux to operate smoothly, even on systems with limited physical memory. Another reason Linux doesn't need 16 gigabytes of RAM lies in its lightweight desktop environments. Unlike heavily integrated graphical shells that bundle animations, background assistance, widgets, and constant network services, Linux offers choice. A user can select a full-featured desktop environment with modern effects, or opt for a minimalist window manager that consumes only a few hundred megabytes of RAM at idle. Environments like XFCE, LXQT, and lightweight tiling window managers are designed for efficiency. They provide essential functionality without unnecessary overhead. On a system with 4 gigabytes or 8 gigabytes of RAM, this makes a dramatic difference in responsiveness. Background processes are often the silent consumers of memory in modern operating systems. Many proprietary systems run extensive telemetry, indexing services, update agents, cloud synchronization clients, and vendor-specific utilities. Linux distributions typically take a more restrained approach. While some user-friendly distributions enable convenience services by default, the overall footprint remains comparatively modest. More importantly, users have complete control. If a service is not needed, it can be disabled permanently. There is no hidden layer of non-removable background processes steadily consuming resources. The Linux kernel's process scheduler also contributes to efficient memory use. It is designed to prioritize responsiveness and fairness without excessive overhead. When memory pressure increases, Linux can reclaim unused pages, swap less frequently used data to disk, or compress memory using technologies like JWAP and SRAM. These mechanisms extend usable RAM capacity without requiring massive physical upgrades. On systems with limited memory, SRAM can create a compressed block device in RAM for swap, effectively increasing available memory through compression. This technique can significantly improve performance on machines with 4 gigabytes or less. Another factor is the absence of forced feature bloat. Linux distributions are not tied to a single corporate roadmap that pushes increasingly heavy system-wide integrations. Instead, they evolve through community collaboration. If a feature adds unnecessary overhead, it is debated, refined, or made optional. This culture encourages lean design. Even full-featured Linux distributions often idle at under 1 gigabyte of RAM usage. Compare that to systems that may idle at 3 gigabytes or more before launching any applications. The difference compounds once software is opened. Software selection also plays a crucial role. On Linux, users are not restricted to one monolithic productivity suite or browser ecosystem. There are lightweight text editors, efficient file managers, minimal media players, and terminal-based tools that consume negligible memory. Even modern browsers, which are often the heaviest applications in everyday use, can be managed effectively. While web browsing itself can consume large amounts of RAM due to website complexity, Linux's efficient memory handling ensures that inactive tabs can be swapped or compressed gracefully. It is important to clarify that Linux can absolutely use 16 GB or more of RAM when available. On high-end workstations, development environments, virtualization hosts, and gaming rigs, additional memory improves multitasking and caching. The key distinction is that Linux does not require 16 GB to function well. It scales upward when resources exist and remains usable when they do not. That adaptability is rare. Many operating systems are optimized primarily for modern hardware with generous specifications. Linux, by contrast, retains backward compatibility and performance on older machines. Historically, Linux gained popularity in part because it could revive aging hardware. Old laptops with 2 GB or 4 GB of RAM that struggled under heavier operating systems often found new life running lightweight Linux distributions. This is not just nostalgia, it reflects architectural choices. The Linux kernel's low baseline requirements, combined with configurable user environments, allow it to operate within tight memory budgets. Even today, minimal installations can run comfortably within 1 GB of RAM for basic tasks. Another advantage is Linux's transparency. Users can see exactly how memory is being used. Tools like top, atop, free, and vimstab provide detailed insights into memory allocation. This visibility empowers users to identify memory-hungry processes and adjust accordingly. In more opaque systems, users may notice high usage but lack the ability to remove or disable the cause. Control over the system directly translates to better resource management. Package management systems also help maintain efficiency. Linux distributions allow users to install only the software they need. There is no requirement to keep pre-installed trial applications or vendor utilities. Minimal base installations can be extremely lean. In server environments, Linux often runs without any graphical interface at all, consuming a fraction of the memory required by desktop-focused systems. This server heritage influences desktop efficiency as well. Security design indirectly supports lower memory usage too. Linux's permission model and separation between user space and kernel space reduce the need for constantly running background security scanners with heavy footprints. While security tools certainly exist on Linux, they are typically optional and modular rather than deeply embedded at every layer. The result is fewer always-on processes consuming RAM. Modern Linux distributions have also adopted memory optimization technologies that further reduce the need for large RAM pools. Systemed, despite debates around its scope, includes efficient service management and parallel startup mechanisms. Wayland, replacing older display server architectures in many distributions, can reduce certain graphical overheads. Mesa's open-source graphics stack is tightly integrated and continuously optimized. Each component is refined incrementally, contributing to overall efficiency. The philosophy of doing one thing well, inherited from Unix traditions, still influences Linux software design. Instead of massive, all-in-one applications that attempt to handle every possible function, Linux encourages smaller, specialized tools. This modular approach often results in lower memory consumption. Users combine tools as needed rather than running a single heavyweight suite. Consider development environments as an example. On other systems, integrated development environments may preload extensive services and graphical frameworks. On Linux, developers can choose minimal editors paired with command-line build tools. Even when using full IDEs, the underlying system overhead remains comparatively low. This means more of the available memory is dedicated to active tasks rather than system background usage. Virtualization and containerization demonstrate Linux's memory efficiency at scale. Containers share the host kernel rather than running separate full operating system instances. This dramatically reduces memory overhead compared to traditional virtualization models. It is common to run multiple containers on systems with modest RAM allocations. The same principle applies to everyday desktop usage. Shared libraries and efficient memory deduplication reduce duplication across processes. Swapping behavior is another differentiator. Linux provides fine-grained control over swappiness, allowing users to tune how aggressively the system moves memory pages to swap space. On low-memory systems, careful tuning can maintain responsiveness even under pressure. With SSDs, swap performance has improved significantly, further reducing the practical need for large physical RAM in basic workloads. Another often overlooked point is that perceived memory requirements are driven largely by modern web applications. Many tasks once handled by lightweight native software now occur in browsers running complex JavaScript frameworks. This trend affects all operating systems. The difference is that Linux itself does not add substantial overhead on top of these applications. If a browser consumes several gigabytes due to heavy web apps, Linux does not compound the issue with additional gigabytes of baseline system usage. Energy efficiency is also connected to memory use. Systems with lower RAM demands can operate with lower power consumption. This benefits laptops and older hardware. Linux's efficient handling of background processes reduces unnecessary CPU wake-ups, indirectly conserving memory bandwidth and power. It is worth acknowledging that certain workloads genuinely benefit from 16 gigabytes or more of RAM. Video editing, large-scale software compilation, high-end gaming, and running multiple virtual machines simultaneously can easily exceed 8 gigabytes. Linux does not defy the laws of physics. Heavy workloads require adequate resources. The point is not that 16 gigabytes is useless, but that it is not a universal baseline requirement for a smooth computing experience under Linux. The perception that 16 gigabytes is mandatory often stems from systems that steadily accumulate background complexity over time. Linux distributions, especially those focused on minimalism, resist that creep. Because the ecosystem values performance across diverse hardware, developers are conscious of maintaining efficiency. There is community pushback against unnecessary resource inflation. Educational environments further illustrate Linux's flexibility. Schools and institutions often deploy Linux on older hardware to maximize budgets. These systems function effectively for browsing, document editing, and programming tasks with far less than 16 gigabytes of RAM. This real-world adoption reinforces the practical reality that high memory baselines are not inherently necessary. The absence of intrusive advertising frameworks and constant cloud synchronization also reduces baseline usage. Linux does not embed mandatory ad services or promotional content engines within the operating system. While optional cloud services exist, they are not inseparable components consuming memory at all times. Even modern graphical effects, when enabled, are typically hardware accelerated and do not impose heavy memory penalties. Compositors manage visual enhancements efficiently. Users who prefer absolute minimalism can disable effects entirely, reducing overhead even further. The broader open-source model encourages optimization because performance improvements benefit everyone. When developers optimize a library or reduce memory leaks, those improvements propagate across distributions. There is no fragmentation caused by proprietary silos. This collective refinement keeps memory usage in check over time. In practical terms, many Linux desktops in 2026 run comfortably on 8 gigabytes of RAM for typical productivity, development, and light gaming tasks. Even 4 gigabyte systems remain usable with appropriate distribution choices. The operating system itself rarely demands more than a small fraction of total memory. The rest is available for applications. Ultimately, the statement that Linux doesn't need 16 gigabytes of RAM reflects its philosophy as much as its engineering. It is designed to respect hardware constraints rather than assume abundance. It treats memory as a resource to be optimized, not consumed by default. It provides tools and choices that allow users to tailor their systems to their actual workloads. 16 gigabytes of RAM can enhance performance for demanding scenarios, and Linux will gladly use it when available. But unlike many modern computing environments that feel bloated without it, Linux remains lean, adaptable, and efficient. Its kernel architecture, modular services, lightweight desktop options, intelligent caching, transparent resource management, and community-driven optimization all converge toward a simple reality. Linux scales with your hardware instead of dictating it. In a world where software often grows heavier each year, Linux demonstrates that thoughtful design can deliver capability without excess. It proves that a modern operating system does not have to demand ever-increasing memory just to remain usable. And that is why, even in 2026, Linux doesn't need 16 gigabytes of RAM to provide a fast, stable, and fully functional computing experience.